Okay, next one for chapter 6 part 2, we're going to talk about carboxylic acid. Carboxylic acid is very applicable to the fatty acid of the triglyceride, yeah? So let's look at this, the objectives. Recognize the carboxylic group in the compound, assign the IUPAC name, okay, explain how the hydrogen bonding affects the physical property of carboxylic acids, understand the key reaction between the carboxylic acids, yeah? Alright, let's look at the first thing first, okay? Structure and the bonding of the carboxylic acid. So if you're looking at the group, okay, is what we have is a carboxyl group, okay? COOH is what we call a carboxyl group. So carboxylic acid contains a carboxyl group. We have a hydroxyl group, again in alcohol, OH. Then we just only mentioned about carbonyl group, C double bond O in aldehyde ketones. And now carboxylic acid, we have what we call carboxyl groups, yeah, COOH. So here comes the confusions, okay. The correct way is actually this one to represent C double bond O, then OH. Alright. Here is delta negative, okay, delta positive, okay, delta negative, delta positive here, and this is a short form of way to represent, okay. C double bond OH is exactly represented here. You can do either here or here. Is exactly represented here, yeah. C double bond O, then OH, okay, not C O O then H here, okay, not this way. It's actually here, C double bond O, OH. Some people, right, they forgotten or see wrongly. They ignore this one. They say that it's a carbonyl group, or they see the other way around, say it's OH group. This one come as a whole, yeah. C double bond O, OH, right? This is what we call a carboxyl group. So carboxyl containing compounds are found abundantly in nature. Okay, for example, what we have lactic acid. Okay, lactic acid is formed in muscle cells during vigorous exercise. Then lactic acid also commonly found in fermented food. Alright, we have citric acid, a very good buffering the agents. Okay, and also give the citrus in the citrus fruits. And then we have fatty acids for the triglycerides. Okay, you can see a very long chain hydrocarbons with a carboxylase group. This is what we call a fatty acid. Yeah, very important. Okay, doing the naming for carboxylic acids, same thing, same as others. All right, we need to find the longest chain. Okay, for carboxylic acid is one of the oldest sort of like very long time already known this kind of compound. So they have common names, like for example acetic acids. Okay, is actually the IUPAC name is called ethanoic acid. Okay, acetic acid is also the vinegar. Alright, butyric acids, okay, the common name, or we call it butanoic acid for the IUPAC. Then citric acid is basically the common name. The correct way of doing the international way is called 2-hydroxyl 1,2,3-propane tricarboxylic acids. Yeah, it's much more complex, but the IUPAC names is a worldwide standardized naming. Yeah, so it's very crucial for you to actually know how to do the correct naming. Common names, please don't get me wrong, still very frequently people are using it. Okay, so but in the scientific literature, it's best to use the IUPAC name, yeah. Then you can bracket the common names over there, okay, just to standardize the IUPAC names in your reports. So these are some of the common names, okay, of carboxylic acids. Okay, you can look at it, okay, from very just 1 carbon to about like 18, 19, 20 carbons over here, yeah. So you can see from here, IUPAC names, we do find the longest chains, okay, and we need to prioritize the carboxyl groups here, COOH. So we need to number from 1, 2, 3, 4, okay, so the methyl group is number 3, so 3-methyl butanoic acid, okay, we change it to oic acid. The carboxylic acid, right, is actually one of the like the big brothers, okay, so it actually takes precedence over most of the other functional groups, including hydroxyl groups, amino groups, and carbonyl groups. Okay, this is for your informations. Okay, don't worry too much about in the exams. Okay, I won't go too deep in this way. Yeah, okay, as long as you know how to do the naming, that's fine. Then if you got more than one carboxylic acid, the carboxyl groups, then we need to write the dioic. If got two, we put it dioic acid. The same goes here, dioic acid. Yeah. Okay, let's try this one. Yeah. Use the IUPAC rules to name the following carboxylic acids. Okay. So what we have here, all right, is 1, 2, 3. So it's a 3 carbons. We got a carboxyl. What we have is 3 carbon is propane. Okay, so it's a propanoic acid. Over here, 1, 2, 3, 4. Bromine at located number 3. So it's 3 bromobutanoic acids. Okay. Okay, let's look at the physical property of carboxylic acids. All right. So again, this one we are talking about the interactions, okay, between carboxylic acids and carboxylic acids here. So you can see over here, all right, carboxylic acid actually forms hydrogen bondings here between the molecules, what we call intermolecular force. Okay, hydrogen bonding, as you know, is very strong. Okay, comparative to dipole force and the dispersion force. And this one is the stronger type of hydrogen bond compared to N and H. Okay, this is O and H because of the larger differences in terms of the electronegative. So it's a stronger type of hydrogen bonding. Yeah. And one thing you can see from here, right, it actually can form 2 hydrogen bonding. Okay, 2 hydrogen bonding between 2 molecules. This is what we call a dimer. And because they form 2 hydrogen bonding, you can see that it's actually a lot stronger compared to just 1 hydrogen bonding. Okay, so you can see, okay, carboxylic acid have significantly higher boiling point because they have polar compounds and form very strong intermolecular force 2 times. Okay, for simple aliphatic compounds, the boiling points usually increase in the order of, all right, we got hydrocarbons, we got aldehyde and ketones. So this one is through dispersion force. This one is through dipole. This one is through 1 times hydrogen bonding. This one has 2 hydrogen bonding, yeah. Okay. So in the graph, usually we just compare here. Here is because it's due to the hydrocarbon chain getting longer and longer. Okay. So this one is actually due to increase in the dispersion force. So we just look at here. The reason why you jump over here is because here got 2 times hydrogen bonding, here 1 time, here is because dipole force, and here is the dispersion force between molecules, okay, between the aldehyde, between alkene, between alcohol, between carboxylic acid, yeah. At the melting point of carboxylic acids, as the molecular weight of carboxylic acid increases, the melting point increases, okay. And with the low molecular weights, usually is quite smelly, yeah, with an unpleasant smell. Okay, the reason is also because it's more volatile. Okay, the smaller the molecule, actually more volatile, yeah, because of the weaker interactions. So it's more volatile, easier to evaporate, so you can smell it. And because of that, plus the inherent the property of the molecules is very sharp. So if you smell some of the short chain fatty acid, it's quite sharp and unpleasant. Yeah, that is also why some of the broken down type of the hydrolyzed carboxylic acids, okay, is being broken down. That sometimes they have this very strong smell. Yeah, okay. Some are naturally occurring type of reactions in the process of preparing your food or the processing of the food, yeah. Okay, so you got undesirable or desirable. Okay, it can be a undesirable smell or the desirable smell, yeah, depending on what is the food, yeah. Okay, looking at the solubilities, right? The carboxyl groups over here and can actually form the hydrogen bonding with water. So here is relatively quite soluble in water, but this hydrocarbon chain is the one that is not soluble in water. Yeah. So as the chain get longer, what happens is that the solubility will decrease. Okay, will decrease here. So you can see from here, you can see initially over here with the short chain one, okay, the carboxyl groups, okay, is strong enough to actually make it soluble in water. But as the hydrocarbon chain get longer, okay, the solubility decreases, okay, until it becomes insoluble in water due to the long chain hydrocarbon, yeah, which is non-polar and dislike water, yeah. Okay, let's look at the key reactions of carboxylic acid. So we have mentioned previously the primary alcohol will form the aldehyde. Aldehyde can be further oxidized to form a carboxylic acid. Okay, if you want to go backwards, it's basically reduction through hydrogenations, yeah. Looking at the acidity of carboxylic acids is actually acidic, okay. Acidic is because it can donate the proton or hydrogen ions, yeah, to form into what we call a carboxylic ions, okay. One thing about this carboxylic acid, right, is that it's a weak acid, okay, like vinegar, acetic acid is a weak acid, alright. Weak acid, as I mentioned in the Chemistry 101, is because it's not completely ionized. Okay, most of the molecules still exist as the carboxylic acid molecule. Okay, only small amount, okay, again, it depending on what kind of molecule, yeah, small amount of the carboxylic acid convert to carboxylic ions, giving out the hydrogen ions here. Hydrogen ion, as I mentioned, is the components that is giving you the acidity. So you can see from here, carboxylic acid groups, okay, in the water, it will be dissociate. Okay, it will dissociate in water to form a carboxylic ions. Okay, and the hydronium here. This hydronium is the one that gives the acidity here. So you got acetic acids. Okay, that are being ionized, okay, to form acetic ions, and the hydronium ion, yeah. This one hydronium, you can either do it like that or like that, yeah. It's really up to you, yeah. But a lot of people, they just write their H plus here. For balance purposes, then probably you need to write their H3O plus. So these are general reactions that shows, okay, that the it's reversible. Okay, again, it can be dependent on the amount of the hydrogen ion as well, or the pH. Yeah, so the pH can actually convert this here or the other way around. High in pH, okay, high in pH means that is your lack of hydrogen ions here. Yes, lack of hydrogen ion. So what happened, right, is that when you are lack of hydrogen ion, what happened? So you're going to take out more of this, okay, away to form here. So it will be favored in this side. But when your solution, low pH, a lot of hydrogen ion in your solution, so the hydrogen will be added into the carboxylate to form a carboxylic acid. So you can actually use the pH to dictate what molecules you want. Higher pH, you're going to have this form. Lower pH, you're going to have this form, yeah? So therefore, the pH of the solution determines the forms in which a carboxylic acid exists in the solution. For example, citric acids in body fluids, okay, favor the carboxylate forms here. So this one you can see in one of your tutorial questions. Okay, fluids, our body, our cells is more or less neutral, 7.4. Okay, 7.4 is considered quite high. So what happens is that these, okay, will convert to the carboxylate. Yeah, that's why one of the questions say why is it in carboxylate is because, okay, of the higher pH. Okay, higher pH, this one will donate, okay, and create that, yeah. So when your pH is very, very low, you got a lot of acidity, so you add back into the molecule to form this, okay. So pyruvic acid is an important intermediate in the energy conversion reaction in living organisms. Okay, as I say, cells is always neutral pH. It's usually called pyruvate because it's commonly in the carboxylic forms. Okay, so you draw the pyruvate, okay, on O. You can either draw that or okay, C double bond O. That's fine. Yeah? Okay, you can actually go through a few reactions here. First is the neutralization reaction of carboxylic acids. Okay, although carboxylic acids are weak acids, they can react readily with strong bases, for example, sodium hydroxides or potassium hydroxides to form what we call salt. There's one thing about this here is that once it's being neutralized to form what we call a salt, okay, with this salt is very, very soluble in water in regard of the length of the R group. Okay, it can be very, very long, but it's still soluble in water. Okay, so for examples, you got the acid, you can neutralize it with a strong base to form a sodium acetate, very, very soluble in water. Or you can benzoic acid react with a potassium hydroxide to form potassium benzoate, very, very soluble in water. So carboxylic acid salts are solids at room temperatures and are usually soluble in water because they are ionic. Okay, the reason why it's also that why is it solid in room temperature is because ionic, very, very strong. The intermolecular forms, they are not separating, they are in solid form. Okay, even long chain acids with extended non-polar hydrocarbon portions can be solubilized in converting them into salt. Okay, you can see here, insoluble after converting salt is soluble. Okay, very, very useful, yeah, very, very useful, yeah. Why? You can see from here, after you convert it to salt, it can, for example, sodium propanoates. Okay, it can be used as a preservative for like all the breads, cakes, and so forth. One of the reasons why is it so useful as a preservative is because the sodium propanoate is so soluble in water that it can go into the cell, bacterial cell, okay, or mold cells and interfere with the internal component of the cell. That's why the bacteria and the mold, right, they will stop growing because of interference. If it doesn't soluble, it cannot go through the cell. Okay, it cannot go through the cell, it cannot be go into the cell, and so it doesn't have effect. Because of this, they convert it to something that is high in solubility. It can enter into the bacteria, it can enter into the mold and stop the bacteria or the mold from growing. Okay, so you got other type of preservative, sodium benzoates. Okay, very, very common food preservative in the food. Okay, for example, cranberry prawns, okay, bacteria ketchups, okay, carbonated beverage, and so forth. Carboxylic acid, right, since it's a weak acid, it can be a very, very good buffer. Yeah, buffer is actually a solution to control the pH, what we call resist the change in pH, because this is very, very important, especially when you are doing formulation for your food products, because you don't want the pH to keep on changing. In your food products, you want to be stable, because the moment the pH change, your product texture, your product the smell and things like that will start to change. Okay. But if you want to make it into a good buffer, again, you need to have a very balanced between the carboxylic acid molecule and the carboxylic ion groups. Okay. Then the carboxylic acid can also form ester. Form ester through reaction with alcohol. Okay, so carboxylic acid react with alcohol to form what we call the carboxylic ester. The carboxylic ester is a flavor molecule. Yeah, it's a flavor molecule. So you can see from here, esterification process between a weak acid and the alcohol, they form the strawberry flavoring. Okay, they form the oil or wintergreen. Yeah. Alright. Yeah, students, it's very important for you to know how to do the reactions for this. Yeah. Okay. So in the exam, it's possible that I give you this. Okay, you need to draw this one, or I give you this, you need to tell me what is the initial product. Alright. So you can see from here, please give the structure of the ester formations to react. Okay, so this one join over, they will form a ester and water. Okay, because it's a condensation reaction, so water will be formed. Yeah, same goes to this, they react, this one go over here, attach, they form this molecule and water. This hydrolysis, of course, you can break it, okay, through using acid, strong acid. You can reverse. In the presence of water and strong acid, you can break the bond, okay. When you break the bond, you will form an acid and an alcohol, yeah. So you can reverse the reactions. Okay, next is what we call the saponification. Saponification is the breaking of the ester linkage. Previously over here is hydrolysis using strong acid. You form back the original molecule, but when you use a strong base like the sodium hydroxide solutions, okay, these will not form back the original carboxylic acid and alcohol. Instead, they form the salt and the alcohol. Yeah, and this, remember, few slides before, very, very soluble in water. Okay, so these are some of the key summary of the key reaction of carboxylic acids. Okay, so what you have here is that the carbonic acid can actually dissociate in water to form an ions. Again, this depending on the solution or the environment pH. Okay, the carboxylic acid, when you react with an alcohol, can form ester. The ester can be broken either through the strong acid or strong base. If you use a strong acid, you form back the original carboxylic acid and alcohol. If you break using the strong base, you will form a salt that is very soluble in water and alcohol. So carboxylic acid, you can also react directly, not the ester, react directly with a strong base to form what we call the carboxylic salt. Okay. Okay, let's look at some of the common molecules. Over here you can see these are some of the common molecules that carboxylic acids. The one that is very common, very applicable is this one, in your food. Yeah, in the food industry, these two are used quite. Acetic acid is vinegar. Okay, and use it for preservation as well. Citric acid, very good buffering agent. Yeah. Okay, so I will stop here for chapter 6. Okay, chapter 6 I break down into part 1 and part 2. Part 2 I got A part and B part. Okay, so make sure that if you got question, please ask in the Padlet. If you got no question, please indicate no question in your Padlet. Okay, thank you very much.